Let's see if you guys can hear me. Let's see if you guys can hear me. Yeah, that seems to be good. Nice. Okay, so today we're gonna carry on with our Pytorch tutorial, deep learning, machine learning series, I guess. Oh, the focus here is not great. Okay, and I'm sorry to be gone for about time, but I had to do some exams in the university, and there was a lot of things going on in my life. But I'm back now, and I'm planning to stream at least one time per week, and I'm trying to carry on with this tutorial, I guess. So yeah, very nice. So let's change scene here. I'm just gonna go and check the preview here. Let's do that. It might be a bit too bright for this camera, so I'm gonna go and fix that as well. I think it's this one, yeah. Filters, color correction, and the contrast. Can we change back to normal? I don't think that's... Yeah, I think that's good. Maybe change it down a bit. Yeah, I think that's nice. Great. Hopefully does this camera not lag too much. I'm just gonna go and check the properties here. What is the resolution of this? Okay, it's not great. Either way, I think this looks fine. Yeah. So yeah. So today we're gonna carry on with our Pytorch tutorial and start with something new. Instead of transform learning, we will do something else. So let's go to Pytorch own documentation and see what they have for us. So we want to get tutorials actually. So we did transform learning for about 30 days ago. And I think it is in this page here. Yeah, so we're gonna do adversarial example generation. So we are basically... so yeah. So if you're reading this, hopefully you can appreciate how effective some machine learning modules are. Research is constantly pushing machine learning modules to be faster, more accurate, and also and more efficient as well. However, an often overlooked aspect of design training modules is security and robustness, especially in the face of an adversary who wishes to fool the module or model. This tutorial will raise your awareness to the security vulnerability of machine learning modules, and will give insight into the hot topic of adversarial machine learning. You may be surprised to find that adding imperceptible perturbations to an image can cause drastically different module performance. Given that this is a tutorial, we will explore the topic via example on image classifier. Specifically, we will use one of the first and most popular attack modules, the fast gradient sign attack, or FGSM, to fool a MNIST classifier, a threat module. For context, there are many categories of adversarial attacks, each with a different goal and assumption of the attacker's knowledge. However, in the general overarching goal is to add that least amount of how does this sound even? Jesus.
Perturbation.
Okay, nice. Perturbation to the input data to cause the desired misclassification. There are several kinds of assumptions of the attacker's knowledge, two of which are white box and black box. A white box attack assumes that the attacker has full knowledge and access to the module, including architecture, inputs and outputs and weights. A black box attack assumes the attacker only has access to the inputs and outputs of the module. and knows nothing about the underlying architecture or weights. There are also several odd types of goals, including misclassification and source/target misclassification. A goal of misclassification means that the adversary only wants the output classification to be wrong, but does not care about the new classification is. A source/target misclassification means that the adversary wants to alter an image that is originally of a specific source class, so that it is classified as a specific target class. So it basically attacks either the image or the entire class, which is, if it attacks the entire class, then we are working on very sketchy eyes. In this case, the FGSM attack is a white box attack with the goal of misclassification. With this background information, we can now discuss the attack in detail. So we have a fast gradient attack, or gradient sign attack. One of the first and most popular adversarial... How does this sound? Jesus. English, hello?
Adversarial.
Adversarial, okay. Adversarial attacks to date is referred to as a fast gradient sign attack. Or FGSM. And is described by Godfellow explaining the harnessing adversarial examples. The attack is remarkably powerful and yet intuitive. It is designed to attack neural networks by leveraging the way they learn gradients. The idea is simple rather than working to minimize the loss. Let's do this instead. Is simple. I'm just gonna go and check this. Nice. The idea is simple rather than working to minimize the loss by adjusting the weights based on the backpropagation gradients. The attack adjusts the inputs data to maximize the loss based on the same backpropagation gradients. In other words, the attack uses the gradient of the loss and the input data, then adjusts the input data to maximize the loss. So it's basically using the whole infrastructure to create the most significant loss for us. I'm also gonna change this camera a bit because it's not that good. Because I have to change the focus here. Let's see if this works better. Yeah, that kind of didn't work out. Okay, that somewhat worked out. Either way, so from the figure X, which is this one, the panda here. This is not good. I have to fix this later. Anyway, is the original input image correctly classified as a panda, and why is the ground truth label, which I think it is this one here, 4x, and the alpha or theta represents the module parameters, and j is the loss. So this is basically the parameters, and this is the whole thing, which is the loss used to train the network. The attack back propagates the gradient back to the input data to calculate this loss then. Then it adjusts the input data by a small step, which is 0.007 in the picture, in the direction of this loss here. That will maximize the loss. The resulting perturbed image, X prime, is then misclassified by the target network as a gibbon, when it's clearly a panda. So basically what they do is they insert some sort of noise to change the picture from a panda to a gibbon, which it's clearly not, because it's a panda. So by doing this, they can attack the machine learning network to think it's a gibbon instead of a panda by using this noise here. Hopefully now the motivation for this tutorial is clear, so let's jump into the implementation. So basically what you do, and I'm gonna do it here, I'm gonna remove this terminal here. So let's create a new folder here, and this should be attacks prevention or whatever. Prevention, let's call it that, and just create a main.py file here. So they import first Torch, so import Torch here, and then they import also the neural network from Torch, dot neural network. So it's gonna be from Torch dot neural network import. No, it's actually gonna be this and as an n actually. Okay. So when we've done that, we also want to import the function, which is import torch dot neural network dot functional functional as f, I guess. Yeah, big F. Yep. And we also want to import the optimizer. So it's torch dot, I think it's optim, right? Yeah, optim as optim, I guess. Optim, right, like this. I can also remove this here. Nice. And we also want to import Torch Vision to use on custom datasets, so that's fine. Import import Torch Vision vision. I think I spelled it wrong. From Torch Vision, import datasets actually. So we want to import datasets and also transformers. Datasets and transformers. Nice. And also we want to import NumPy so we can do some simple math calculations. So NumPy as np, np, that, and we also want to import the matplotlib function, which is gonna make us able to plot certain functions and things. .pyplot as plt, right? Yeah, okay, so basically what they say is, in this section we will discuss the input parameters for the tutorial, define the module under attack, then decode the attack and run some tests. Inputs. There are only 3 inputs for this tutorial and are defined as epsilons, lists of epsilon values to use for the run. It is important to keep 0 in the list because it represents the module performance on the original test set. Also, intuitively, we would expect the larger the epsilons, the more noticeable the perturbations, but the more effective the attack in terms of degrading module accuracy. Since the data ranges here is between 0 and 1, which is the probability of choosing the right name for the right image, no epsilon value should exceed 1, which is quite clear, to be honest. Pre-trained module, which is the path to pre-trained minutes module, which was trained with this example. For simplicity, download the pre-trained module here, so we're going to use that. We also want to use CUDA, boolean flag to use CUDA if it's desired and available. Note that a GPU with CUDA is not critical for this tutorial, as a CPU will not take much time. But that's fine. So we will essentially write this, and I will also see if we can use CUDA. We should be able to use that. So we have the module here. Now this is not going to work at the moment because I have to install a module, but I want to test CUDA first before we do anything else. So let's just type print, and we want to print GPU if let's see, I think it's torch.cuda is available, right? Yeah. Else we want to print the CPU. So this should be like that. If this works and we get the GPU, we have CUDA installed. So let's see. So we have GPU. Nice. So CUDA is installed. Very nice. That's not really a requirement for this tutorial, but it's fine. So let's install this pre-trained module then, because we're not going to build our own. We could do that, but that is not a requirement for this tutorial, so let's fix that. So we're gonna download the module here, which is this one here. Interesting. So data.pkl, and it's searching for this minutes data. So it's inside data, which is here. Oops. Interesting. Let's download this. It's interesting that they use a Google Drive, but either way. So I think that's that. We can probably open that with the archive manager, and here we have that version, and here's 01. Okay, so interesting. How does this work? Let's go into our file explorer and see how it is defined in our file explorer. So here we have this. We probably want to extract it here, so let's extract here. And we have this folder here, and I'm gonna move this into the our working folder. So let's do that. Go to home. We are in Pytorch tutorials, so it should be here, and this should be inside of the attacks prevention, and paste it in here. So that should be fine. And if we go into our VS Code, we will probably have this folder here. Yeah. So it's obviously going into this and searching for this Leonard mist minist model.path, which we don't have. So I don't think this is gonna work, but let's see if this works. Okay, it kind of did. Interesting. So yeah, let's carry on with the tutorial and see if this actually works. That's interesting. Either way. So it should be... we might want to print this seed, so we just know it works. So let's do that. Like that. And see if we get the same result as they get. Yeah, we did. Nice. Okay, so module under attack. As mentioned, the module under attack is the same minist module from this examples minist. You may train and save your own minist module, or you can download and use the provided module. The net definition and test data loader here have been copied from the minist MNIST example. The purpose of this section is to define the module and the data loader, then initialize the module and load the pre-trained weights. So we have to essentially create our own class and do this, and see if this works. I think it will do though. So let's do that. This should be here, right? Yeah. So we're gonna create our own class, which is gonna be net, and this is gonna be a submodule from nnn.module. We also want to define an init function, which is gonna initialize the whole class. Gonna do that, and this is gonna take itself, so this will be a sub function, and we also want to call the super of this net, so we call the super module, and it's gonna take itself as well, like that. Dot init, so we will initialize the super class, basically. And I'm just gonna copy these here. So here we essentially create the different layers of the neural network. This will essentially create the different layers in the start, and then what the neural network with these layers will do is essentially the forward function here. So this will use the forward function. So we create the real use, the max pool 2D, and self dropout, all of these functions here. So we also want to, and this is going to be outside. So this is the test loader. We will get the data from the torch vision, which is this one here. So this will get the data and the test loader, and then we want to define the device we want to use, which is either going to be our CPU or GPU, but we also know that that is, in fact, in our case, going to be our GPU, because we already test that. We can remove this print up here. We don't need that. So here we have our CUDA available, if that's true, and then we set the device to either CUDA or the CPU. Then we add the module to, we set the module or the class to our device, which is going to be our GPU here. And then we're going to load the pre-trained module. So this is going to load the pre-trained, oops, that is not what I want to do. I guess that's what I want to do. Yeah, that's definitely what I want to do. Oops, that is not what I want to do. And then we want to evaluate the module. So if our downloads actually worked correctly, this is going to be fine. And I think I want to have our terminal up here, so I'm gonna move this bash up here. So we have to cd into our project files here. files like that, and also go into attacks, prevention like that, and we have main.py here. So we're gonna type python 3 main.py and execute and see if there is some warnings, or it seems to be working. We're downloading the data and see if this will train actually. So it didn't train because we haven't found the .path, which is the pre-trained module. So we have to check that out, and I think I installed it wrong. It should be said download the pre-trained module here, but if I go to this, we get here and let's see, main.py train. I think this is in fact the module. So I could technically just copy this whole thing and we have the module, and we also have to train it. We can do that. So let's do that. So let's go in here, go here, and I will also inside of this attacks prevention folder, we want to create a file called module.py and basically copy this whole thing. By the way, all this code is going to be on GitHub, so you guys can go back to it later if you don't follow along. That is super fine. So let's try to run this module.py file, and then we will get our pre-trained module, basically. I think that should be fine. I hope this is connected to our CPU. It seems to that it is. So we're training the module already. This should take not too long because we use our CUDA drivers. I wonder how many epochs there is. I might actually be able to check that. It's gonna see if there are any hyperparameters somewhere. It seems that like it isn't. So it's gonna save the .path file somewhere here. I will find out later. But I don't see any hyperparameters that specify the epoch value. Let's do this instead. Epoch. Where is this defined? Okay, so it's basically just takes in. Okay, so where is this train function defined or used? I mean, it should be used somewhere in the bottom, I think. Okay, so here each epoch args.epoch. Let's see if this actually is still. I think there's probably about 10 epochs, I think. So let's check that. This will take a longer time if you use your CPU, but I use my GPU, so that's great. I think it's gonna be like 10 epochs or something. I would bet on that. So let's see, we are in the 9th epoch. The accuracy is 99%, by the way, so that's really great. That's good. And see if it's... So we're on the 10th epoch right now. Let's see if this works. I hope this camera is not too blurry. It might be. It's alright. I will fix that later. So there's more than 10 epochs. I wonder what the amount of epochs are, in fact. It doesn't specify that. Args.epoch, where's args defined? Optimizer. I would genuinely want to know how many epochs there is. I hope it isn't 100, because then it will take a reasonably long time. 13? Nope, 14. I wonder also where this will be saved at. Is it /data or is it... No, it should just be named this. Okay, nice. Okay, so it's saved somewhere. I wonder where it's saved. So it's saved. The module is saved either way. module.state.directory, and then they added this. So they save the object. F is the file like. Let's see if I can find that. It's inside data. Maybe it's inside of here. No, it's not. Docs. Nope. Data here. Minced. Okay, let's do this then. Let's go into our Nemo or File Explorer and see if we can find this file. Pytorch tutorial, data. It might be in this one, raw. They didn't specify where it was going to be saved. Choose a program, I guess. No, we don't want to do that. Version should be 3, yeah. Data is here. This is a binary file, so we don't want to open that. That is just some reasonable code. So where does this being saved at? Okay, that's just a readme. So that's great. They haven't really specified the module. That is their bad. Interesting. It should be here. And if you download that, you basically come to this. Maybe maybe I did that so wrong. Maybe it's because we don't want this .pt. What if I can change that to maybe this file name and then just use that? It's a bit weird. It's a bit a weird of way to do that, but let's try that out. Pytorch tutorial, project files, attacks prevention, add that file here. And then I just have to change the file path in the main.py file. It should be just this one here. Let's see if this works. I'm gonna clear this and run the main.py file. Let's see if this works. Okay, that kind of worked. Interesting. So we have done that. That solved the problem. Then I can remove this whole minis file here. We don't need that. Great. So just rename this, download this, and rename that. That would be great. So yeah, and we don't need this module.py file either. So we have our pre-trained module here. That's great. So let's carry on with the tutorial and see if this works. I'm gonna move that and go back here. Okay, so as mentioned, wait, it should be up here. As mentioned, the module under attack is the same mnist file or module from the example. You may train your own whatever. And this worked as well. So FGSM attack. Now we can define the function that creates the adversarial example by perturbing the original inputs. The FGSM attack function takes 3 inputs. Image is the original clean image, which is X, which is going to be this panda image up here. And epsilon is the pixel-wise perturbation amount, and this is just the loss. And data underscore grad is the gradient of the loss. And the input image is this here, which is going to also be the loss. The function then creates the perturbed image as perturbed image equals the image plus epsilon, which is this noise, multiplied with the value, which is going to be 0.007, which is equal to the image plus basically this. This is all mathematical function behind this. You don't need to remember that. Finally, in order to maintain the original range of data, the perturbed image is clipped to range 0 and 1, which is probably the most reasonable value interval to have, because this is just a probability vector, or probability values, which is between 0 and 1. So they will create a function which is gonna attack the data on our pre-trained module. So let's do that. Just paste it here. And this restores the tensor to original scale, which means that we can basically compare two images, one that is a change or attacked, and one that is the original. So testing function here. If we go down here, finally the central result of this tutorial comes from the test function. Each call to this test function performs a full test step on the minist test set that reports in final accuracy. However, notice that this function also takes an epsilon input. This is because the test function reports the accuracy of the module that is under attack from an adversary with strength of epsilon. More specifically, for each sample in the test set, the function computes the gradient of the loss. The input data underscore grad creates a perturbated image with this function attack, or the function that is going to create the attack. The perturbated data then checks to see if the perturbated example is adversarial, so it checks if the image is attacked. And in addition to the testing the accuracy of the module, the function also saves the results from some and returns some successful adversarial examples to be visualized later, so we can compare the two images, which is real nice. And this is all the test function. I'm gonna copy this and just go through it for you guys. I'm gonna post it in the same file. It doesn't really matter. And I opened freaking a web browser. So this test takes in the module and the device, the test loader, and also the epsilon, which is gonna be a value. So the correct value is also gonna be initialized as 0, and adversary examples is obviously gonna be an empty list, but this is the list we're gonna save all the images, so to speak. So we're gonna loop over all examples in the test set here. So we're gonna loop over the data target in the test loader, and this is basically saying add the data and the target to the device. Set the required grad attribute of tensor imported for attack. So we need back propagation for this attack to work, otherwise it won't work. And then also the output is going to be module with the data. So we forward pass the data through the module, and in its predictions we're going to output the max, and we are going to keep the dimensions, and the one is going to be fine. Get the index of the max log probability. So we're going to get the maximum probability. If the initialized prediction is wrong, don't bother attacking, just move on. So basically, if the initialized prediction is wrong, we don't do anything and we just carry on with our function here. And calculate loss. So this will basically calculate loss. 0 all existing gradients. So we're going to start over here and calculate the gradients of the module in backward pass. So we're going to do a backward propagation here with the damaged image from the attack, basically. Collect the data grad, so we collect the data, basically restore the data to its original scale. So we denorm the data, so we restore everything. Call the attack. So we basically do the module from free from attacks here, and then we call the attack here. Reapply normalization to get the values between 0 and 1. And then here's the output with the perturbated data normalized. And check for success. So we're gonna find the final predictions from the output.max function, and we're gonna get the same dimensions and so on. And the final So if the final prediction item is equal to target item, then we're gonna add one specific cache for saving 0 epsilon examples. So if epsilon is equal to 0 and the length of adversary examples is less than 5, adversary examples is perturbated data.squeeze. So we are basically putting the data together with the other data. And then we have adversary examples.append. So init predictions.items, we append all these data. And if the final prediction is not equal to the item target or the target item, we basically just say the adversary examples for visualization later. So we basically save everything here. The final accuracy is divided at the correct, which is going to be added every loop, divided by the float of the length of test data loader, and here it basically prints the epsilon and the test accuracy and whatever. And then return the final accuracy and the adversary examples. So we're going to run the attack. Last part of the implementation is actually to run the attack. Here we run a full test step for each epsilon value in the epsilon's input. For each epsilon, we also save the final accuracy and some successful adversarial examples to be plotted in the coming sections. Notice how the printed accuracies decrease as the epsilon values increase. Also note that the epsilon equals to 0 case represents the original test accuracy with no attack. So basically, when the epsilon increases, that means the attack increases, which is also increasing the noise. So if we copy this, which is basically initializing the accuracy, accuracy list and also the example list, and then we run tests for each of these, we will get these type of values. So let's go and run this and see if this works. So we use CUDA, that is true, available, good. And see if this somewhat crashes. Boom, epsilon 0. So this will take some time. It doesn't print out every test or every epoch, so this will take some time. But you can see accuracy is almost, it's actually 99%. So if this epsilon is increasing, the accuracy will decrease. And that is basically showing how that hex works. And we will go through the attack later. So boom, you can see that it decreases by a lot. So it decreases by 3% with just an increase of 0.05 of the epsilon, which is really interesting. So let's see if it increases even more. I'm just gonna check the audio here. Increase even more. I'm just gonna check the audio here. Yeah. Okay, so let's see how this works. Okay, so now it is on 0.1, and we have decreased it by 10% already, which is quite a lot. Let's see if we get another epsilon here. Okay, so with 0.15, we decreased it by like 20% right now. So by just increasing like the noise by like 5%, it decreases like with 5% of the accuracy, which is interesting. So yeah, you can see that the accuracy actually decreases when the epsilon is increasing. So now we have 50% accuracy, which is super bad. And if we go and check on this function here, we essentially collect the element-wise sign of the data gradient. So we collect the data gradient .sign, create the perturbated image by adjusting each pixel of the input amount. So we basically take the image, which is a set of pixels, and add some values to it. So we basically just add values to values which is based on a pixel, and then we technically change the pixel a little bit by adding the value to it. So when we manipulate the pixel basically, and by doing so we also decrease the accuracy. So when we are in the 0.25 epsilon, we also have a test accuracy of 25%. And as you guys can see, this is the epsilon, and this is the original data. So this is backpropagation data, this is the original image. So we take the epsilon, which is 0.25 at the moment, and multiply that with the backpropagation, add it to the pixel values of that image. That is basically what this function is doing, and it's super easy function actually. So it's really interesting to prevent this type of attack. And if we, so if we have an epsilon of 0.3, which is 30%, we decreased it to 14% from 99%. So by just doing this function, by adding 0.3 to the backpropagation data, and then add it to the pixel values of that image, we basically degrade the test accuracy but with like 80%. And keep in mind that the epsilon here is just 0.3. What if you add epsilon with 0.5? It will be disastrous, especially if that image that is manipulated is used to essentially train the module itself even more. So it's basically like a cancer inside of the machine learning by just adding some values to the pixels of the image, which is really interesting. So yeah, so the result here, the first result is accuracy versus epsilon plot. As alluded to earlier, as epsilon increases, we expect the test accuracy to decrease. This is because larger epsilons mean we take a larger step in the direction that will maximize the loss. Notice the trend in the curve is not linear, even though the epsilon values are linear spaced. For example, the accuracy of an epsilon, which is 0.05, is only about 4% lower than the epsilon, which is equal to 0. But the accuracy of epsilon 0.2 is 25 lower than the epsilon of 0.15. Also notice the accuracy of the module hits around accuracy for a 10 class classifier between epsilon, which is equal to 0.25, and epsilon, which is equal to 0.3. So we can see here, and this is the graph made by Pytorch themselves, is that this function here is basically not a linear damaging. It is actually somewhat like a second grader, maybe, if it goes up or down, or it's not linear at least. So it's a parabolic, I guess. So if we plot the differences, you will see like this image here, and so let's check if we get the same plot here. So let's run this test again. This will probably take some time so let's run this again here. You know what, I will just run everything at a time because this is gonna take too long otherwise. So let's do that. So this is basically showing this plot. This will just show the accuracy and with the epsilon values, and this will actually show you the image distortion. Whoops. So let's run this one more time, and then we're basically finished with this tutorial. And the code will be up on GitHub, and I will also try to publish this code on my website, so you guys can go and check that out if you want to. The website and the GitHub is down in the description, so just feel free to go through it, and so on. It's a rather quick tutorial, but it's really worth noting if you're gonna build a machine learning module. You have to, especially if you want to use images. But yeah, so let's see if this goes. I'm gonna go and play some Snake, maybe. It might be actually not worth. Let's go and play some Snake, whatever. Or see if we can play some Snake here. Play. Just wait for it. Oh no, okay. I'm super bad at this. Jesus. Let's see if this is going somewhere. Okay, let's carry on. Oh my god, that is just terrible. So we're just waiting for our module to run, and I'm playing Snake while it's running, basically. I'm super bad at this. Jesus. Come on! Oh. Nice. We got 2. Let's go. Oh. Ah, shit. Okay, let's see if this is done. Almost done, but you guys can see that the epsilon value is increasing and the accuracy is decreasing, in fact. Really good to know. So if you're using some image classifier, if you're in your machine learning network, this is probably something that you will try to fix. So let's see if these images is in fact showing. I think we have 2 epsilons left. It goes up to 0.3. So let's see if that is in fact the case. Come on, I can play this like this. And by the way, I recommend you use your GPU here, because otherwise it won't be as fast. Okay, boom. Okay, so here we have the graph, basically, from the test, and as you guys can see, we have like a epsilon value of 0 here, and then we have epsilon value of 0.05, and then we have epsilon value of 0.1, and so on. So you guys can see that this is in fact a function here. Let's see if I can remove this. And boom, here you have the distortion of the images. So basically here, here's the epsilon value of 0. It's fine, we have like a 7 to 7, 9 to 9, 0 to 0, 3 to 3, and 5 to 5, right? And here we have an epsilon value of 0.05. So you have a value of 2. It thinks it is in fact a 8. Here we have a 1, but it thinks it's a 3. Here we have a 3, but it thinks it's a 5. So already at 0.05 it's bad. And then it just becomes worse. And here we have, like, this is clearly a 0. You guys can see that, but it thinks it's a 2. This is actually a 7, but it thinks it's an 8, so you guys can see. So already at 0.05 it's bad, because it gets the wrong output. And it doesn't really matter if you go lower, because it's already bad. So here you guys can see that this is a problem for machine learning modules, and you really have to check if this actually is happening to you if you have a machine learning network that is published through a web server. So that is really something interesting to look at. And if we go back to our test here, you guys will see that this is the same result as we got before. So where to go next? Hopefully this tutorial gives some insight in the topic of the adversarial machine learning. There are many potential directions to go from here. This attack represents the very beginning of the adversarial attack research, and since there have been many subsequent ideas for how to attack and defend modules or machine learning modules from an adversary. In fact, at NIPS 2017 there was an adversarial attack and the defense competition, and many of the methods used in this competition are described in this paper, which is here. I can link this paper also in the this is a long paper, but I will link that in the description as well. So that is, if you are planning to build our network like this, you probably want to read through this document, because otherwise this will in fact happen to you. You will get these bad values. Like, this is fine, the top here is fine, but if you go to the second row, this is already bad, because we have a 2 but it thinks it is a 8, we have a 1 but it thinks it's a 3, we have a 3 but it thinks it's a 5, and so on. And it doesn't really matter if we go lower, because it's all wrong values. So that's really interesting. Yeah, it's really all that. So another direction to go is defense is different dimensions. Adversary research is not limited to the image domain. Check this out: attack on speech-to-text modules. So say, for example, Siri or Alexa. This could be something that you might want to be interested in. So this is attacks on speech-to-text. So this is really interesting to go through. It's really just a page about a document on 7 pages, so it's really nice to go through. I will also link that in the description. So you guys can check that out. Oh, whoops. Let's go here, and I think it was here, yeah. The total running time of script is 4 minutes, but I think we actually don't use the GPU here. It really depends on what type of device we are using here. Let's go and check for the device here, just to be sure. Device, CUDA, if it uses CUDA. So that, okay, so this, oh, whoops, I just changed the text here. So we actually use CUDA. I recommend you use CUDA, not CPU, because otherwise it will take too long. So yeah, this is really just a tutorial today. I will do some more tutorials later, but this is really something you want to look into. So yeah, thank you guys for watching, and have a great night.